Okay. So let's start by naming a few of these compounds here. Remember, at this point, we just know how to name alkanes and as well as what we call alkyl halides, which are alkanes that have a halogen bound to them. Okay. So the first step, as always, is going to be to find your parent chain. In this case, it's these 4 continuous carbons, right? The longest continuous set. So my parent chain would be a butane. I'm going to identify my substituents, which in this case is this chloro group right here. All right, so this is a chloro. I got to number my parent chain, and while we're still getting good at that, you can number it both ways and then decide whichever one puts your substituent on the lowest possible number. So we can go 1, 2, 3, 4, or 1, 2, 3, 4. So in this case, the blue numbering scheme is the one that we're going to use because it puts that chloro group on carbon 2. So this would be 2-chlorobutane, all one word. Run it together. I know I kind of build it from the back to the front, but that's just kind of the way that my mind thinks about it. So for this next one, again, we're going to have to find the longest continuous set of carbons. So 1, 2, 3, 4. Actually, I'll be consistent with my coloring. Parent chains will be pink. 1, 2, 3, 4, 5, 6, 7. But you know what I'm going to do is to just double check, because this is a pretty long thing sticking up here. So 1, 2, 3, 4, 5, 6, 7. It actually wouldn't matter which one I decided to make my parent chain. I would get the same answer either way. And you can kind of do it both ways to convince yourself of this. But let's just leave it as this one is my parent chain. So again, I said that it was 1, 2, 3, 4, 5, 6, 7. So that means my parent chain is a heptane. I'm going to identify my substituent, which has 1, 2, 3 carbons. So in the chat, what would a 3-carbon substituent be called? All right, okay. Make sure we all got it here. So this is a propyl group, right? Prop was our 3-carbon prefix. Stick the YL on it because it's a substituent. And then we're going to number our parent chain both directions. You'll notice in this case, it really doesn't matter which numbering scheme I pick because they both put that propyl group on carbon 4. So 4-propyl heptane. Again, run it all together, all one word. Okay. For this next one, again, I'm going to do my parent chain is in pink. That would be 1, 2, 3, 4, 5. Don't forget to count that carbon at the base of that fluorine. Okay, so my parent chain is a pentane. I have, 2 fluoro groups on there. All right, and then in terms of my numbering scheme, I'm going to have to go in both directions here. So everybody in the chat, what do we think? Do we need the red numbering scheme or the blue numbering scheme? All right. I don't know if half y'all are asleep or just pissed off we're back online, but yes, it is indeed the blue numbering scheme, because of this one right here is what does it for me, right? That's going to be the lowest possible number. The other group is at carbon 3 no matter what, but I want to make sure to have the lowest possible numbering scheme. So remember that since we have two of them, we're going to have to include both the location of both of them. So this would be 1, 3, and then difluoropentane. I stick the di out front. If there was 3 fluoro groups, it would be trifluoro, 4 fluoro groups, tetrafluoro, et cetera, et cetera. All right. And then for the last one, just to kind of practice in a different representation, again, I really like the bond line because it's way easier for me to draw, but nonetheless, we want to get good looking at these other representations. If you find one representation easier than the other, then just convert it, right? Because we should be able to freely convert between the different representations. That was one of the skills that we got in chapter 1. So again, I got to find the largest continuous set of carbons. That's the name of the game. So if I went 1, 2, 3, 4, 5, all right, that way I have 5. But if I go 1, 2, 3, 4, 5, 6, that's going to have to be my parent chain because that is the longest continuous set. So I have a hexane as my parent chain. I have this 2-carbon substituent here. So this would be an ethyl group. All right, so it's the exact same game as we did in all the other representations. It just looks a little different. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. In this case, I'm going to pick the red numbering scheme because it will put my ethyl group on carbon 3. So 3-ethyl hexane. All right, so we want to work with both alkyl substituents, those that are just carbon and hydrogen. So for an example, a propyl group or an ethyl group, as well as we learned how to deal with the halogen substituents like a chloro group or a fluoro group. All right, I will say that there's like a special type of alkyl substituent. So for example, if we had something like this, this would be my parent chain, my longest continuous set of carbons. My parent chain is a heptane. This is a branched alkyl substituent here. Okay, and there are only a few of them, but they do have their own kind of special name. This would be an isopropyl group. And it's located on carbon 4 of my heptane. So this would be 4-isopropyl heptane. These are thoroughly explained in that second video that I posted on the substituents of the alkyl halides, or of the alkane nomenclature. I'll also say that in the assignment, I posted this kind of cheat sheet here because I'm okay if you like, basically, I'm not going to ask you all the other problems we did are totally fair game for an exam or a quiz. I'm not really going to worry about you memorizing all these branched alkyl groups. If you're given a kind of cheat sheet like this, you want to be able to use it. But again, you can sort of download this and use this as you're answering your problem set. I don't really care if you have memorized what an isopentyl group is, for example. But these are all the different ones. They all have special names just to kind of show you. A propyl group obviously has 3 carbons. An isopropyl group has 3 carbons as well, but it's just in a little fork. Okay, a butyl group has 4 carbons. An isobutyl group has 4 carbons, but there's that fork on the end. Same with the pentyl and the isopentyl. Okay, so if these don't ring a bell at all, you want to make sure to watch those videos that I posted, right? The intention was that everybody sort of would have already had their introduction to nomenclature before this week. Okay. A few more rules that I'll explicitly go over here just for the sake of review. Kind of started off basic last time. There's two more things that we want to consider here. And that is what happens if I have two different groups on my. So let's say we have something like this and like this. How do I name this compound that has these two different substituents? Okay, so first few steps are all the exact same. You're going to go through, find your parent chain. 1, 2, 3, 4, 5, 6, 7. So my parent chain is a heptane. Okay, I'm going to identify my substituents. I have a fluoro group here. And I have a chloro group. Use a slightly different color down here. All right, so now I have these two different substituents. This next step is the exact same. We're going to number our parent chain to figure out the locant of all these different substituents. 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. Again, until you get good at it, you can kind of do it the long way. So my blue numbering scheme would have this, my substituents at 2 and 5. My red numbering scheme, it's 3 and 6. So the blue numbering scheme wins. Okay. Now, how you put these together when you go to, so this is now, we know that this is a 2 fluoro group. And this is a 5 chloro group, right? When we go to actually build our name, what we do is to put our substituents in alphabetical order. Okay, so when I list this name, it doesn't matter what numbers are associated with them. I'm going to list the fluoro group first and then the chloro group. So this, because, oh, I lied. I don't know my alphabet. I'm going to list the chloro group first and then the fluoro group, right? Because C comes before F in the alphabet. So even though this one has the higher number, when I go to build my name, I always put them in alphabetical order. So 5 chloro, 2, I didn't leave myself nearly enough room, 2 fluoro heptane.
What if it's like an isopropyl versus like a butyl group or something like that? If would we go off of the iso part, or we would go off the like the methyl part? The iso, if it was isopropyl, would we go off the P and compare it to the B, or would we go off the I and then compare it to the
you would go
B?
off the I. So actually, I'll tell you what, it's actually even a little bit more of a pain in the butt than that. For the isopropyl groups, you go off the I. I didn't make the rules here, but these are it. And this is sort of why I'll give you the cheat sheet as well. For the isopropyl groups, you go off the I. But for the sec butyl and the tert butyl, it's the B. I don't know why. But yes, for all those iso groups, you go off of the I in terms of the alphabetical order.
Okay. And then one more question. It was on it was on that first page. It was the one with the it was the fourth problem. On the hour homework, there was like parentheses with subscripts on it. What does that mean? Like I don't know if we went over
and subscripts.
Yeah, like it was on the endpoints on like the CH3s. It was like CH3 and then parentheses and then like a subscript with like 2 or 3 or whatever.
Oh, okay. Yeah,
I didn't understand that. I don't know if we went over it.
It's a good question. So, whoops. It would be CH3, CH3, 2, something like this. Wait, is this right? Yeah. So you'll notice if we start building like going like a Lewis structure sort of thing, CH3, Whoops, that's not a C. CH, you notice that this carbon is missing actually 2 bonds. And so what this is saying is those 2 bonds correspond to 2 different methyl groups. So there's a CH3 here and a CH3 here. So what it's really saying, I mean, long story short, it's saying that there's 2 of those particular groups bound to that previous carbon.
Okay, that makes sense then. All right, thank you.
Yep, so like this, again, what's kind of pictured here in green, this is one of those groups and this is the other group, just to kind of color code. This middle one is this. Yeah, they'll, again, I mean, kind of like all this stuff, you'll get good at it as you sort of practice. When you're first starting out, when in doubt, start drawing out the actual Lewis structure and making sure your carbon has all of the correct number of bonds. That's kind of the fail safe, right? Carbon always has those 4 bonds, no matter which way we're drawing our structures. Okay.
So that one would it would create the isopropyl bond line then, right? Or no? No, huh? Wait.
No, this would be 2-methyl. So this one would be, and you can convince yourself of this, 2-methyl propane. So you kind of have to have a big chain in order to get an isopropyl group, so that, because otherwise those carbons are like part of the backbone. So just because you see a fork doesn't mean there's like an isopropyl group. It's always going to be a substituent on kind of a much larger chain.
Okay. All right. Thank you.
Yep. Okay, so when we build our name, we put it in alphabetical order. So let's do a little bit of practice real quick just to make sure that that all makes sense. Sucks to get the numbering right, the name of the substituents right, and then put it all together and do it a little bit wrong. So let's just make sure we got it. All right, so everybody take a second and see if you can't give me what the name of this one would be. I will say, while you're working on it, nomenclature is one of those things that at first seems very overwhelming because there's a lot of rules, but then we just keep on doing it over and over and over again throughout the semester. So by the end of the semester, y'all will be experts here. All right, so if you think you got it, go ahead and put it in the chat. Let's see who's, we got any rock stars here. All right, so I'm just going to blaze through this one real quick because we got to move on. But yes, so parent chain is indeed octane. 1, 2, 3, 4, 5, 6, 7, 8. My numbering scheme, I'm going to pick the numbering scheme that puts that I have the lowest numbers. That would be this direction. And importantly, when I go to build this name, so this is a 5-ethyl and this is a 2-methyl. I'm going to make sure to put these substituents in alphabetical order. So it is indeed the 5-ethyl that comes before the 2-methyl octane. Okay. The other thing I want to note is you'll see in these names, and actually all the names that we've done, the only time you have dashes is to separate the letters and numbers. So it's never going to be something like methyl dash octane. If it's two letters, you just run it together. The dashes are only there to separate numbers and letters. And you do need a dash anytime you have a number and a letter in there together. Right, so yeah. Okay, one more, and this is the sort of special case, worst case scenario kind of deal, is what if we have something like this? Where we're going to go through, we're going to identify, the first few steps are always the exact same. You're going to identify that you have a pentane as your parent chain, and that your substituents are this fluoro group and this chloro group. All right, and then you're going to go through and number your parent chain both directions, 3, 4, 5. So on my red numbering scheme, I have a 2 and a 4. If I go the other way, 1, 2, 3, 4, 5. My other numbering scheme, I also have a 2 and a 4. So remember, in all these previous examples, these are a good collection of examples here to illustrate these two important points. You always go for the lower numbering scheme. That's the first thing you do, right? So that's why it was 5 chloro and 2 fluoro, as well as 5 ethyl and 2 methyl. We just made sure we had the lowest possible numbering scheme in there. But now we have a situation where our numbering schemes are tied. Okay, so the tiebreaker is alphabetical order. Okay, if there's no tie, you don't consider alphabetical at all until you're constructing your name. But if there is a tie in our numbering scheme, the tiebreaker, and again, this is specifically for numbering, is to put it in alphabetical order. So this one would be 2 fluoro, 4 chloro. One of the biggest mistakes that I see people make is to always think that you're doing it in alphabetical order. Remember, in these two examples, we didn't consider alphabetical order until we were constructing our name. It didn't influence our numbering scheme at all. It's only in this example where we have a tie in our numbering scheme that we're going to put them in alphabetical order, that we're going to number them in alphabetical order, rather. All right, the names are all, oh my gosh, I just messed it up. I don't know why I have a problem thinking oh my gosh, okay. It's the exact opposite of what I just did right there. It's 2 chloro, 4 fluoro. I messed that up twice thinking fluoro comes before chloro. Yeah, I don't know how yeah, it's early. C is indeed before F. I think I'm thinking that fluorine's the smaller one on the periodic table, but anyways, alphabetical order. So it would be 2 chloro, 4 fluoro. I'm making sure you guys are paying attention here. So yeah, so again, you can sort of note that in both of these, we constructed the name in alphabetical order, but it was only when we had a tie in our numbering scheme that we numbered them in alphabetical order as well. All right, my bad. I know that was a mistake. Go for it.
So on the previous example where the answer was 5 ethyl 2 methyl octane, let's say there was an ethyl group on the 7th position. In that case, the numbering would run the opposite way, and we would have to actually name it from it would be 2 4 ethyl.
At that point, so I understand what you're saying, and yes, all of a sudden there's a tie. When there's it, so there has to be a tie in the numbering scheme, like completely. Okay. Now the only problem with the example that you're suggesting is you can't really have an ethyl group on carbon 7 because all of a sudden your parent chain wouldn't include that one. It would include these two here. Right, so we can't have long substituents on like the second carbon, or we would just have to change what we make our parent chain. I'm trying to think of an example of what you're getting at here. I mean, the bottom line is you have to have a tie in the numbering scheme. If there's any sort of, if you number it both ways, and at any point there's a lower number in there, you would pick that one. But if you have a tie across the board, 2 and 4, 2 and 4, then you result to alphabetical order to break that tie. Again, like you want to have in your mind that it is a tiebreaker to resort to alphabetical order.
Okay, thank you.
Yeah. All right, so now we're going to move on to cyclohexane, or really just the cycloalkanes. We're going to start with cycloalkanes. And these have in the name what's going on here, that we are talking about cyclic alkanes. So you can take a second to convince yourself they look like shapes. I mean, they are shapes, but they look like we're in geometry class here. All right. And so these would be cyclopropane, cyclobutane, cyclopentane, and this one is cyclohexane. So let's just convince ourselves real quick. They all start with cyclo because they are all cyclic. They also contain the information about the number of carbons in each ring, right? So cyclopropane has 1, 2, 3. We have that prop substituent, or not substituent, prefix on there indicating 3 carbons. Cyclobutane, but is 4. Cyclopentane, pent is 5. Cyclohexane, hex is 6. You can keep on going. They get much harder to draw. Actually, octane's not too bad. Cyclooctane. Anyways, I'm not very good at drawing above cyclohexane, but we can also have cycloheptane, cyclooctane. Okay. So anyways, these are now going to be cyclic alkanes. Okay. When we have a cycloalkane with just like one substituent on there, so we'll sort of bypass these bigger ones for right now. Again, the most popular one, the one that we're going to spend a lot of time talking about, I kind of teased why that is at the end of last class, but is cyclohexane. So now if we have, let's say, a methyl group on there, we sort of have this logic of numbering the ring in the same way that we would number a chain, where we want that substituent to be on the lowest number, right? So this, when we start numbering, this would be 1, I don't know, let me just go in a circle here. Okay, but when we actually go to write the name, this would just be methyl cyclohexane, right? So a lot of people are tempted to put the 1 on there. To be honest, I don't think it's the greatest sin in the world. If this was like an exam, you would still get the vast majority of the credit because you understand what's going on. But the actual correct answer would be to drop that 1. Okay, so why is that? Well, because if I were to, let's say that I moved this methyl group over here, it doesn't become 4-methyl cyclohexane. I just change my numbering scheme. So now I start numbering so that this is carbon 1. So if there's only one substituent, you know it's always on carbon 1. So there's this sort of, there's not this ambiguity to it where you have to specify the carbon number. If there's only one substituent, it's always going to go on carbon 1. So you just don't put it. If you have more than one substituent, so for example, something like this, now all of a sudden you do have to now all of a sudden you would include the numbering scheme on there. This is carbon 1, 2, 3, 4, 5, 6. So this would be 1,3-dimethyl cyclohexane. Okay, so because now all of a sudden, since it's a dimethyl, you could have 1,2-dimethyl cyclohexane or 1,4-dimethyl cyclohexane. There's no longer, where you don't have to specify it. You now do have to specify it because those are all different. All right, so the first one would just be methyl cyclohexane. The other one is dimethyl cyclohexane. All right, this one, everybody take a second and convince yourself that this would be 1,3-diethyl cyclohexane. Whether you number clockwise or counterclockwise is just to make sure that you have the lowest possible numbering scheme. So I could, for example, go 1, 2, 3 in order to number this one. It actually would be the same the other way, but make sure that you're putting those lowest possible numbers. So diethyl cyclohexane. Okay, but again, if there's only one substituent, I know it's a little weird, but we just drop that one because it's always going to be one. Okay, so now get to new stuff. So this is what we call Cis Trans Isomerism. Okay, and so basically what this is let's say that I have a molecule like this. Everybody take a second and name this one for me. Put it in the chat once you got it. Yeah, nice. Run it all together into one word. And we got to remember it's a site. We got to put, our parent chain is now this ringed structure. So this would be 1,2-dimethyl cyclohexane. Okay. Remember to include that cyclo in there because now your parent chain is in that ring. So this actually has, this is not as drawn. This is not pointing to exactly one molecule. This actually points, could be one of two different structures that are drawn. Okay, either a, whoa, that was terrible. What we would call the cis structure or isomer, or the trans isomer. Okay, this pair is a pair of what are called stereoisomers. Right, so we learned about constitutional isomers previously, or structural isomers, same thing. This would be, for example, 1,2-dimethyl cyclohexane or 1,3-dimethyl cyclohexane. Those would be structural isomers because there's a different connectivity of atoms. Here, everybody's bound to the same, everybody's neighbor is the exact same. There's no difference in terms of connectivity of atoms. But these do have different, what are called stereochemistries. They are not identical molecules. So let me show you, or let me explain, for example, what these bonds mean, because this is our first time seeing these. This wedged bond represents a bond that points out of the page. So when you see a bond that's a wedge like that, you imagine that it's sticking up at you. And the dashed one is the exact opposite. It's terrible. These point into the page. So these dashed and wedged bonds are a way of like conveying the shape of these molecules in more detail. So if we look at our cis isomer, our cis stereoisomer, both of those bonds are pointed up at us. That's what that's representing there. Both of those methyl groups are sticking up at us, right? So they're both kind of like pointed in the same direction, pointed up. If we look at our trans isomer, one's pointed up, one's pointed down. Okay, so the connectivity of the atoms are the same, but the overall geometry of the molecule is not identical. I can't like superimpose these molecules onto one another in any way. So the full name for these two molecules would include their stereochemistry. So cis 1,2-dimethyl cyclohexane and trans 1,2-dimethyl cyclohexane. On the cis isomer, both of those substituents will be pointed on the same side. On the trans isomer, they will be pointed on opposite sides. Okay, so actually, all right, so actually let's just get good at identifying cis and trans isomers real quick. Okay, so anyway, if you've kind of clicked ahead on this cyclohexane homework assignment, you'll see these dashes and these wedges, and that's what they mean. So again, a dash, the solid line, means that that bond's like sticking up and pointing out at you. The wedge, you imagine that that bond is pointing into the page, so it's pointing away from you. Okay, so if I look, and we'll like I know I've been beating cyclohexane to death. Let's do an example with cyclopentane. Right, they don't have to be on adjacent carbons. So everybody see if you can't give me the full name of these, including those stereochemical designations of these shapes here, of these molecules here. Ooh. All right, so stereochemistry is kind of something that we can tack on to the end of our nomenclature responsibilities here. The first steps are always going to be the same here, where we identify our parent chain. In this one, it's the cyclic structure. So this is a cyclopentane. I'm going to identify my substituents. I have 2 methyl groups here. And they're located 1, 2, 3 carbons apart. I can just double check that that's indeed the nomenclature scheme I want by going the other direction as well. Now the blue numbering scheme gives me bigger numbers. So I'm going to stick with the 1, 3, the red numbering scheme. So we have 1, 3 dimethyl cyclopentane. And now to complete this, I'm going to look at the stereochemistry of the molecule. I'm going to notice that one bond is pointed into the page. The other bond is pointed out of the page. So this one would be trans 1,3-dimethyl 1,3-dimethyl cyclopentane.
I have a quick question.
Yeah.
So would the cis have the locant priority?
So when you're doing the locants, the numbering scheme, you don't consider cis trans at all. It's all about just making sure that you have that lowest possible numbering scheme. So in the case of these cyclic molecules, I wouldn't want the blue one, because in blue, it would be 1, 4. And in red, it would be 1, 3. So that's why I chose red. I'm not factoring in the stereochemistry into that decision. Does that answer your question?
Yeah, thank you.
And then if I were to be asked like to draw the stereoisomer, so now if I want to draw, whoops, that's not how you spell that, stereoisomer, I'm going to draw the cis version of 1,3-dimethyl cyclopentane. And so what I'm going to do is I'm going to turn those bonds either into 2 wedges, or I could do them into dashes as well. Both of those would represent a cis structure where those 2 bonds are pointed in the same direction. It's kind of terrible drawing skills here today. All right, but both of these would be the stereoisomer. They're actually the same molecule, just like if you imagine picking it up with a spatula and flipping it over. That's all I've really done here in terms of my drawing. But these would both be the cis isomer of 1,3-dimethyl cyclopentane. Okay, so in my next example here, do I have the cis or the trans isomer? Okay, so it doesn't matter if they're both wedges or if they're both dashes, both of those indicate they're pointed in the same direction. So this would indeed be the cis isomer. All right, so if I go through the whole thing, I'm going to identify my parent chain as a cyclobutane. I have these 2 methyl groups as substituents. And they're located 1, 2 apart. So 1, 2 dimethyl cyclobutane. Okay. And just to close it out here, I've been kind of uninventive in that I've always been using methyl groups. They don't have to be methyl groups. So for example, And let me just show you how that would look. Okay, this would be cis 1,2 diethyl cyclohexane. So notice that how this is going to look is that first bond is going to be drawn as a dash or a wedge, right? And it's specifically drawn that way to indicate the particular stereochemistry. And then from there, you just have your normal kind of bond line thing going on. So those are two ethyl groups right there, or two ethyl groups or two carbon substituents, one right there and one right there. So after that first bond that's drawn in that dash or that wedge to indicate stereochemistry, the other ones are just drawn in our normal kind of like bond line structure there. All right, so it looks kind of weird at first. You have this intersection of this skinny line with this dash or this wedge, and you just want to make a note that there's a carbon at that intersection, just like if it was two normal straight lines. All right, so let me get everybody's name in the chat here for attendance, and then we will just pick up with this discussion of cyclohexane. On Friday, I'm going to incorporate kind of what we were discussing about the axial and the equatorial positions of cyclohexane into what we were just talking about here. All right, but I'm done with y'all. Sorry that we're back on Zoom till the end of the week. My bad. I'll get better and we will be back in person on next Monday.